Okay, everybody, I think we should probably get started. I think we've waited enough time probably to catch most of the people who went to the other venue at the other end of campus. My name is Mike Fick. I'm a professor here in physics and astronomy. I think I was asked to introduce this morning's talk because it's a little bit more of a science talk. It's a science of are there other Earths like our own Earth, and this happens to be also my research area. This is, in fact, why Dr. Wiseman and I have crossed paths many times at conferences over the past, more than 10 years, actually. Quite a bit more, perhaps. But, of course, she's also here to talk about other issues, and that's something that's open this morning. But this is more of a science talk than the spiritual side of our interests. Dr. Wiseman was an undergraduate at MIT. And she, after that, went down the street, basically, or actually up the street to Harvard for her PhD. After that, she had two very prestigious fellowships in the U.S. She was, first of all, a Jansky Fellow at the National Radio Astronomy Observatory. Was that in Charlottesville you were at? Yeah. Charlottesville. And then she got a Hubble Fellow, which is an even more prestigious, I think more prestigious fellowship, which she held at Johns Hopkins, always along the East Coast. So you must like the snow. No, it's going to snow today here. My punishment for something else. So without any further delay, except handing over the microphone here, this is the microphone for the video at the back. She has another microphone so you can hear her. But we'll spend a moment or so getting this sorted out, and then Dr. Wiseman will spend about 30 minutes telling you about the science she's really interested in, and then she'll have about 30 minutes for questions and answers. A long time today. This is mostly supposed to be a question and answer period. So thank you for coming today.
Okay, welcome. How many of you were at my lecture last night? Anybody? Okay, very good. How many of you are coming tonight? Come. All right, very good. So this morning's lecture is a little more informal. And I'm hoping to introduce some of the topics that I will talk about a little more in depth this evening. So if you can come out tonight, if you're interested in these kinds of things, I hope you can come and continue the discussion. So I want to talk today about this intriguing question of, is there another Earth or other planets that could be like Earth or could support life, this kind of thing. Now, we've all grown up watching all kinds of science fiction films and TV shows, and we have read books that have made us sort of think that surely there are countless intelligent civilizations out there who are either out to befriend us or out to destroy us or something or other. So we've thought about this a lot in our imaginations, but something has changed over the last, about 15 years or so, in that we're actually starting to detect that there are, in fact, planets orbiting other stars. We never really knew that for sure until now. So this has created a big change in that what was more sort of our speculation and imagination is turning into the reality of being able to do scientific studies of planets around other stars. So I'm just going to spend, the next maybe even 20 minutes or so telling you a little bit about this field of exoplanets, we call them. Sometimes it's called exoplanets or extrasolar planets, meaning planets outside of our solar system, and how we look for them and what that might mean for us. And tonight I'm going to talk a little bit more about the philosophical and even religious aspects of this in terms of, what does it mean if we find life elsewhere? Does that affect our view of our own significance as intelligent beings on this planet? Or what if we don't find life anywhere else? What if we are, in fact, the only place in the universe with life? What does that mean? Those are interesting questions. I must now ask the question of, do we have a pointer? I forgot about that, and I can live without it. So if there's not one handy, let's just see if I can use this as my pointer. So this is Earth, if you haven't noticed. That was taken on one of the early moon missions, orbiting missions, I think. Watching moonrise is quite spectacular. In fact, many of the images that I'm using in all of these presentations I'm giving this week are easily found on a website called hubblesite.org. And it's a wonderful site. You just go to it and click on Gallery, and you have the most beautiful pictures of space that you can imagine, and you can study what they are or make them your wallpaper on your computer, whatever you want to do. So that's a nice site I like to tell people about. And then if you want to understand more about exoplanets and the whole program that we have with our NASA space agency and how that relates to other nations and parts of the world working together on this problem and this interesting issue of studying extrasolar planets, you can go to this website called planetquest.jpl.nasa.gov. All right, so let's do a little overview. Those of you who were at my talk last night remember seeing this. This is the Hubble Space Telescope. We put telescopes in odd places where they are away from interfering lights or interfering electromagnetic radiation of any kind, or above clouds where we can get a real dry and crisp view of the heavens. So this telescope was put in orbit, and some of the pictures I'm showing you are from Hubble. I've worked on Hubble for years, so it's near and dear to my heart. We talked last night about galaxies. Galaxies are collections of hundreds of billions of stars and all the intervening gas and dust interspersed between the stars. Galaxies are huge collections of stars, and when we are looking at our own neighborhood, we're looking at a tiny little fraction of our galaxy. We believe that we are in a spiral galaxy, much like this one, that has several spiral arms. And our system is embedded in one of those arms. We call it the Orion arm. And when we look around from our neighborhood, our little nearby neighborhood, we can see several of these dense dark clouds where new stars are forming. That's my own background research as well. And what we are finding is that when stars form, they tend to form with a disk of material, rocky debris and stuff left over in orbit around that young star. And we believe that planets form out of that leftover debris. So one of the hot sciences right now is the study of debris disks around very young stars that have just formed out of these big gas clouds of gas and dust, studying how planets can coagulate over with that leftover material as it sort of gravitationally sticks together. These are stars. I showed them last night, but I just want to remind those of you who saw it and tell those of you who haven't seen this that stars come in all sizes, and they are beautiful to behold. I like this picture because it's a cluster of stars where all the stars are at roughly the same distance from us, so we can see that there are bright stars and dim stars. The brighter ones here really are brighter. They're not just closer, they are brighter. And the colors here represent not only what appears to me to be beautiful gemstones, but also different temperatures of these outer layers of stars. The cooler outer stars with cooler outer atmospheres tend to be redder in color, and the hotter ones look bluer. So we can see a variety of stars here, and one of the things we're trying to study is if different kinds of stars are more or less capable of harboring planetary systems. You know, are different kinds of stars more or less friendly for having planets, and in particular habitable planets around them. In fact, in our galaxy, we think there are about 200 billion stars. This is an infrared image of stars near the center of our galaxy, and so you can see that there are an enormous number of stars. This was done with a telescope project called 2MASS, a survey of stars in infrared wavelengths where you can actually see many of the stars that otherwise would be hidden behind dust and gas in the center of our galaxy. So it really shows you the enormous number of stars. And one star in our galaxy is our sun, and our sun has planets, and we know that one of those planets has life. And so as I advertised last night, we want to know if there are other planets in the universe and if there's another Earth out there. So what are exoplanets, and how do we find and study them? An extrasolar planet, or an exoplanet, is a planet that's outside our solar system that's orbiting a star other than our sun. And several hundred of these have now been detected, mostly indirectly orbiting other stars. And I'll explain what I mean by indirectly. It's very, very difficult to observe a planet around a distant star. A star is very bright. A planet is very small. And it's very dim relative to the star, because planets do not radiate their own visible light. They only reflect light. You know, think about that. When you're looking out at Jupiter and Saturn and so forth, the only reason you see them is because they are reflecting the sunlight. The sun's going up to them, bouncing off, and we see them. If you're trying to find a planet that's reflecting its starlight around another star, it's a very dim object, very small, and it gets lost in the glare of this very bright star. So detecting them has been a kind of detective endeavor over the past decade and a half or so, and I'll explain some of these techniques that have been used. So far, because of these techniques and the technology limits we have, the planets that we're able to detect are not Earth-like. It's not that the Earth-like planets are not there. It's just that we haven't had the technology yet to find things that small around another star at the distance of Earth that Earth is from our sun. So we are getting there, though. It's a very exciting time because we're just right on the cusp of being able to find out if there are, in fact, Earth-like planets around sun-like stars. This whole situation is changing very quickly. And, of course, that leads us to ask some of these more intriguing questions. What if we're not the only life forms out there? So, what if we find a planet that's habitable, that has what is needed to support some kind of life? One of our highest goals right now is to develop telescopes and detectors on those telescopes that can directly detect. In other words, take a picture and characterize Earth-like planets around stars that are like our sun. And we should be able to do that within the next decade or so. So we're right here at this very interesting time in human history where we're about to be able to answer this question that we've had for so long in humanity. We will look for signs of life, and especially primitive life, because we sort of think that's more likely to be the first thing we would find than some of these more intelligent civilizations that we have seen on television shows. But we need also spectroscopy to do this, which is taking the light that we can see from these planets and spreading it out into its constituent colors and seeing if we can see evidence of chemistry in the atmospheres of these planets that would indicate the presence of an atmosphere, the presence of water, the presence of methane, the presence of things that would support life or would in fact tell us that life processes are actually happening. Now, the other end of the spectrum are people that are actually looking directly for intelligent life. This would be the Seti program. Anybody heard of Seti? Yes? Okay, so Seti is the Search for Extraterrestrial Intelligence. And this is a group of researchers that is not bothering to sort of look for signs of algae and bacteria. They want to start the other end and listen to see if there are intelligent civilizations actually so advanced that they are sending out signals of greeting to us that we might be able to receive. So they have radio telescopes tuned to precise frequencies that they would guess that these civilizations might use in order to transmit a message to us. And they are searching the sky. They've been doing it for quite some time. They haven't detected anything that looks like a recognizable signal of intelligence yet, but they are just starting because the number of wavelengths and wave bands and directions that you might want to look is enormous. So this is truly a needle in a haystack program. So these are kinds of the two extremes of this field, looking for already advanced life civilizations that are reaching out to us, and looking for any signs of habitability on any planet that we find around another star, even for the most simplest life forms. The NASA efforts are more on the former, and the SETI program is a privately funded enterprise. What about these distant worlds? We aren't the first ones to think about this. Greek philosophers thought about this already, and there's an Epicurean philosophy. Epicurus from 300 BC was thinking about this, speculated that there are infinite worlds, both like and unlike our own. And we must believe that in all worlds there are living creatures and planets and other things that we see in this world. So it was already speculating that there were other worlds. They didn't quite understand how our galaxy and solar system was arranged, but even by what they knew from looking up at the heavens, he was speculating that there must be other worlds. And then in medieval times, we also had speculation. Giordano Bruno said in the 16th century that he speculated that there were countless suns and countless earths, all rotating around their suns in exactly the same way as what they knew then, the 7 planets of our system. The countless worlds in the universe are no worse and no less inhabited than our Earth. That was a pretty profound thought for the 16th century. So this was an amazing line of thought that was already going on. Of course, this guy was burned at the stake, so I'm not sure that it was real smart. I don't think he was burned at the stake for this statement, but he was pretty outspoken about other things that tended to get him into trouble. So we scientists have to be a little careful sometimes. And of course, more recently, we have our imagination, and Hollywood is very good at imagining what it might be like to look for life in alien worlds. So how do we detect exoplanets? That's the first step. We need to find out if there are, in fact, planets around other stars that could harbor life of any kind. And the indirect technique that's been used the most is to look for motions of the star. If you can't see the little bitty planet around the star, then you want to see if that planet, through the mutual gravitation of the planet and the star, is causing the star to wobble. Because you see, when a planet is orbiting a star, what's really happening is that both the planet and the star are orbiting what's called their center of mass, which is the product of their mass and distance from that center of mass. So what happens is that the star ends up wobbling around that center of mass, which is very near the center of the star, and the planet orbits around that center of mass, and it takes it around the star. So we have a system where both bodies are orbiting the center of mass, and that creates a stellar wobble. That's one way of detecting a planet, and that's been the most successful way to date. There's another thing you can do if you happen to be fortunate enough to be in an orientation toward that star where the planet is transiting between you and the star. So it's actually orbiting around the star, but crossing your line of sight toward the star every time it orbits. And during that transit, and I'll show you some images of what this looks like, that planet will eclipse and will cover some of the star so that the total starlight appears to dim periodically every time that planet goes around. So you may not, again, be able to see the planet, but you can see that starlight periodically dim a little bit due to that transiting planet. That's a very popular technique right now. And then, of course, what we'd really like to do is to take a picture, to image the exoplanet. And that, as I mentioned, is difficult because you have to somehow suppress this huge starlight in order to see something that's 10 orders of magnitude dimmer than the star. So it's really a difficult thing to do. Here is what sort of graphically a stellar wobble can look like if it's wobbling in the plane of the sky. So this would be the track of a wobbling star seen astrometrically. Astrometry is a way of measuring positions of stars very, very carefully. And so you can see in this swirled pattern here on the right, the apparent pattern of motion of a star that's being tugged around by an orbiting object. So the other way that is more often used right now, because our astrometric precision right now is not very good until we get an astrometry mission into space, we use the wobble along the line of sight to measure this motion of the star, and that's called looking for Doppler shifted motion. We talked about it last night. You guys know what Doppler shifts are? Anybody? Doppler shifting is the apparent shift in the frequency or the color, the wavelength of the light of an object you're looking at due to its motion toward you or away from you. So when something is moving away from you, it will be emitting its light at a certain wavelength or a certain color. But because it's moving away from you, as it's emitting that light, the actual frequency that you receive will be stretched out a little bit, and you'll get a longer wavelength or a reddened color on the receiving end than was sent from the object that was emitting the light. And the same as it's moving towards you, you actually receive light that appears a little bit bluer than what it was when it was emitted. Now, if you can watch that periodic change in some object that's first redshifted and then neither redshifted nor blue shifted, then blue shifted, then back again in a periodic fashion, you can say that that object is wobbling in the sky. And you can tell then, by doing a calculation about that wobble, that exactly what kind of planet must be tugging on that thing. So tugging of stars and stellar wobble is a very popular means for detecting planets around them. And soon, of course, we hope to have telescopes that can take pictures of these planets. Who's studying the wobble of stars? Well, there are quite a few astronomers. This is a famous one here is Jeff Marcy down on the left here. But they're using all kinds of telescopes, most of them on the ground. The ground-based telescopes are good enough to do this kind of detection of wobble, especially for stars that are being pulled by large planets. So big Jupiter-type planets will exert a greater pull on the star, and you can actually detect that wobble. Again, we don't quite have the sensitivity, even for these types of telescopes, to sense that tiny little wobble that would be caused by something as small as an Earth-like planet. But this technique is getting better and better. All right, here's how it works. Here's the scientist looking at the happy star. And let's see if the happy star will give us some there. The happy star doesn't like the scientist, so is moving away. And so we get red-shifted light as the star moves away. And then as they become friends, the star moves closer, and you see a more blue-shifted color of light, and so forth and so on. So the scientist is actually looking for specific spectral lines in the light from that star. Hydrogen, for example, gives particular frequencies of light, so you can actually look at that pattern of light frequency and measure it against a calibration source and watch that pattern shift to the red-shifted and to the blue-shifted and measure the wobble of that star. Here's another way of looking at it. You have the star wobbling around, this is greatly exaggerated here, but wobbling around a center of mass that's usually somewhere inside the star, and an unseen planet that's orbiting also and creating that mutual tug on that star. And we don't see the planet, but we observe the wobbling of the star. However, the planets that we're finding are really not good candidates for life so far, because our technology has been limited to seeing these sort of very large gas giant planets. What we would like to find are planets like Earth that have evidence of life or even microbial or tiny life. Most of our discoveries are big things like Jupiter or Saturn, or they're in the wrong location. This picture here is, of course, not to scale about how our planets are distributed here, but you can see what's represented here in this little lane is representative of something called the habitable zone. The habitable zone is thought to be the region that's not too close to the parent star, such that it would be so hot that any liquid water would evaporate away, boil away, and not too far away so that any liquid water would be frozen. Because every life form that we know of on this planet does require liquid water. Even the strangest life forms require some sort of liquid water here on this planet. So to start with, as we look for life, we want to look for a place where liquid water can exist. And most of the planets that we're finding so far are not Earth-sized planets. In fact, none of them are Earth-sized planets in the habitable zone of their star. But that's where we're trying to aim here. Many of these new planets are too cold or too hot to support life, or they have some strange elliptical orbit where sometimes they're very close to the star, sometimes they're too far away, or they're near a star that's very different than our sun, that is so active that it might cause problems for life. Finding another Earth won't be easy. Earth-like planets are small. Whoops. And they're close to bright stars. The kinds of planets, this is Jupiter, the kinds of planets we've been finding are kind of like Jupiter in their size. We're looking for something like Earth. That's the challenge, technologically speaking. You can think of the brightness as a lighthouse. So stars are 1 billion times or more brighter than the planets that we want to look for. So you see the little light next up there? That's supposed to represent a firefly next to a lighthouse beam. So the little firefly gets hidden in the glare, and that's the problem that we have. But once we are able to do this, let me go back just a minute. What we're doing in the laboratory where I work at NASA's Goddard Space Flight Center and in other NASA facilities is to try to find a way to block out that starlight so that you can see the dim little planet next to it. We use things called, for example, coronagraphs. A coronagraph is an instrument that you can put inside a telescope that will basically block out the object that you're pointed at and allow you to see things around the edge. It's not so easy when you have something that's this bright and something this dim, because light can refract around objects, and you have to actually build a very complicated coronagraph device in order to get the kind of light suppression that you need. We're working on different techniques in my lab. One of them is called interferometry, where you actually take multiple wave fronts of this incoming light and you use them to kind of null each other out by sending them on different paths and then combining them together in such a way that they cancel each other out. That's a clever technique. There's another technique that's being developed that's called occulters, where you put a star shade way out in front of the telescope, tens of thousands of kilometers away, that will basically block the light of the star, so that only thing that gets past it is the dim planet light that goes into the telescope. That's never been tried before, but it's another technique that in some sense is simpler than building a complicated coronagraph inside the telescope. So these are technological hurdles that we are facing today in astrophysical telescope development. But eventually, if we can actually directly detect the light from a planet, we want to find out if it supports life. Well, how do we know if it supports life? Well, that's also a detective technique. We want to know, for example, if there's ozone. Ozone, as we know it, is produced by plants and algae on this planet. So if we could see spectral lines from ozone in the light spectrum of a planet, that would be an interesting, what we call a biomarker, evidence that there's biological activity going on that planet. Of course, we want to know if there's liquid water, and you can see water spectral lines in the spectrum. That doesn't mean that there's necessarily life if we find liquid water, but it would mean that that's evidence that the planet might be capable of supporting life. We're quite interested. Here's what a spectrum looks like down here on the left, where you could see evidence of water and oxygen and carbon dioxide, things that either emit special frequencies of light or absorb special frequencies of light, and you can see it in the total spectrum of light that you pick up. And of course, living organisms can produce output including methane. Cows are especially good at that. So we may find a bovine planet someday if we find a lot of methane. So that would be good. All right, so we want to look for evidence of oxygen, water. We can also actually see from the total light itself, we can see whether or not there are interesting things in the atmosphere, biological activity. And of course, you always want to be able to rule out whether there's some other activity. So we have, for example, found evidence of methane on Mars, our neighbor planet. Does that mean there's life on Mars? Maybe. There might be life buried underneath the features of Mars that's emitting methane that comes out. But we also know that methane can be produced by geological activity. So we have to be very careful that we study exactly what kinds of emission that we're seeing and from where, and rule out any other explanations. We're putting telescopes into space. They help out. I talked a little bit about this last night, but when you put a telescope into space, it can often give you a much crisper picture of what's going on. So this is, I showed last night, the Eagle Nebula here. That is one of these regions with star formation where young stars are turning on, and the light from them is starting to clear out the gas between the denser regions of interstellar gas. And these denser columns that are left behind tend to be hot spots for continuing star formation. Well, you can see the difference in quality between a very good ground-based telescope on the left and the Hubble on the right. So it really does help to get telescopes into space. In this exoplanet business, it's especially important to get the telescopes into space because that is where we need the most sensitivity, is looking for these extrasolar planets. We can do some of the Doppler shifted work from the ground, which I showed you with these ground-based telescopes such as the Keck interferometer up on the upper right there. And also the large binocular telescope, which will be built, is going to be operated and is operating on the ground here. But we have space-based telescopes that are going to take us more into the Earth-like planet realm. We're getting ready for this. That's one of my lab's functions, is to design new telescope capabilities. These are artist conceptions of what future planet-finding telescopes might look like. The one on the right is an interferometer, where you have several telescopes working together to give you a sharper image than a single telescope alone could give you. All right, so what does it look like, these different methods? The transits, as I told you about, are when the planet actually happens to be orbiting along your line of sight. So the planet goes in front of the star. The total starlight, which you see in the little graph on the bottom, drops as the planet goes by, and then the total starlight you see goes back up again when the planet gets to the other side. So if you see that happening periodically, you can surmise that a transiting planet is probably in the system. NASA has just launched last year a telescope that's looking only for transits around planets. It's called Kepler, named after a famous historical scientist. And Kepler is looking at a cluster of bright stars in our galaxy and just staring at them and watching to see how many of them have these periodic dips in their starlight. And from that, we will be able to come up with statistics of how many stars have planets and what sizes of planets. The transiting method can tell you something about the size of the planet that's orbiting it, because the amount that the light is reduced depends on the size of that eclipsing planet in front of it. So Kepler, as it operates for the next few years, will be able to tell us some of these statistics. Now, these stars that it's looking at are so far away because they wanted to find a cluster that had many, many stars that it could get at the same time. But they're too far away to do detailed follow-up work. So when we find transiting systems with this telescope, we won't be able to do some of the detailed spectroscopy that we would like to on nearer systems. But it will tell us for the first time statistics about whether solar systems are common and whether Earth-sized planets are common. There's an artist conception of Kepler, but it's actually launched and functioning very well right now. In fact, it's already, even though it's only been up for a few months, it's already found 5 transiting planets. Now, these are planets that are not like Earth, and they're orbiting very close to their star, because it takes, for an Earth-like planet to go around a Sun-like star all the way around in one orbit. How long does that take? That's right, it's 365 days. It takes a year. So if this thing's only been up there a month, it's not had enough time. You really need 2 or 3 orbits to confirm that you're really seeing an extrasolar planet. So it's going to take years before we see the Earth-like planets around in orbits that are in similar to Earth-like orbits around their star. But what we're seeing now are the quickies, the ones where the planet is close in to its parent star. And the closer something is to its parent star, the faster its orbits. That's one of the laws of orbits, thanks to Kepler, that we know about, Kepler the scientist. And so we're seeing these planets that are very close to their parent star, so they're probably very hot, and they're orbiting around that parent star in a fast enough pace that we can see them right off the bat. So these are the first 5 discoveries of Kepler that have happened just in the past recent few months. And you can see that their orbital period below is nothing like Earth. 3.2 days, 3.5 days, 3.2 days, 4.9 days, as opposed to our 365 days. So these are, can you imagine doing an entire orbit around the star in that amount of time? It's really quite incredible. But you can see the light dips. The little graphs there represent the amount of starlight and how it dips every time that planet orbits in front of its star. These are the sizes of these planets that Kepler has initially found. And we say size as opposed to mass because it takes a little more information to determine the density so that you can actually determine what the mass is. But you can tell the size of the planet due to the amount of dipping in the flux of the starlight. So there's our friend Jupiter over there. And these other planets, 4 of them are much bigger than Jupiter even. One of them is smaller than Jupiter, but it's still much bigger than Earth, which is over there on the right. But we're hoping to find Earths. We've just started with Kepler. Okay. That's the transit technique. We're hoping to have a mission of some kind that can do more precision astrometry, which is looking at the stellar wobble in the plane of the sky. If you do that instead of this radial velocity wobble, you can actually tell something about the mass, get a better handle on the mass of the planet that's causing that wobble, because you get 2 dimensions of information in astrometry. So measuring that motion is a goal that we have. And this is our friendly scientist measuring the astrometric motion. There's a mission concept that's being discussed now called the Space Interferometry Mission that could do this kind of work. And then, of course, taking pictures is the next goal, and these concepts I mentioned to you before are also under discussion. One of the common names for this type of future telescope is the Terrestrial Planet Finder, because you want to find a terrestrial planet and be able to discuss it. So one of the things that's happening in the U.S. right now is a full year of contemplation by our National Academy of Science to decide which telescope concepts are the highest priority for the nation to do. We can't afford to do them all. And exoplanet missions are being discussed like this, as well as some other types of telescopes. And we'll find out later this year what we can perhaps afford to build in the near future. My lab is hoping for an exoplanet mission. There's our scientists trying to block out the starlight so that we can see the dim planet around it. That's coronagraphy. And I want to just tell you, we're already finding directly imaged planets. This ugly thing, which I showed last night, is the result of coronagraphy on the Hubble Space Telescope, where there have been instruments where you can block out the starlight and see the surrounding material. It's not quite good enough to see Earth-sized planets on the Hubble. But this particular image shows you this Fomalhaut system. Fomalhaut is a star system. In this image, the star has been blocked out, and that radial material is just noise from this technique. But that ring is real. There's a ring of dust around this star. And when I was working at NASA headquarters several years before, we did a whole press conference on how it was interesting that this ring of dust, the center of the ring, was not centered on the star. So there's the center of the ring, and there's where the position of the star that's been blocked out in this picture. You would think that this ring of orbiting dust should be centered on the star. And the only thing the scientists could figure out due to their models is that there must be some kind of planet that's shaping both that sharp-edged rings. Planets can shape rings in this sense, in the same way that moons around Jupiter and Saturn can shape and cause those sharp-edged rings around planets in our own solar system. And that planet would also cause a sort of shift in the center of the whole system, so that the shift of the ring center to be offset from the star was also evidence of a planet. So we had indirect evidence of the planet already just from looking at this ring system. And then last year, the planet itself was actually seen buried in that ring as we compared old data with more recent data from 2004, 2006, and then further epochs beyond. So we can actually see this planet now. It just looks like a blob, but it's very exciting. This is the first time we've ever taken a picture of a planet around another star. Now, this thing is big. It's a Jupiter-sized thing, and we're probably seeing the hot dust around, or hot dust and gas around this planet. And about that same time, there was another announcement of another Jupiter-type planetary system seen around another star. So we're starting to see planets directly, and that's encouraging for our hopes to see an Earth-sized planet sometime. We also study in my lab how planets form, and we study these dusty, gassy disks that exist for a long time after a young star is formed, it still has this equatorial disk of material around it, out of which it formed. And as the gas in this disk gets kind of blown away by the starlight, the harder, rockier stuff sticks around and starts to coagulate, and this is called a debris disk. And we believe that planets coagulate out of debris in these debris disks, and we can see them in different stages. So we have scientists who are deeply involved in studying how planetary systems form around stars. And we have telescopes that are better tuned at studying that circumstellar material. Here's the Spitzer Space Telescope. That's an infrared space telescope looking at material like this. We also have plenty of ground-based telescopes that are used for this kind of study, in particular radio telescopes. I use the Very Large Array out in New Mexico, this big array of 27 telescopes that's particularly good at looking at dense gas around young stars as they form. Just to summarize, and I'm going to close this part, and I went over a half an hour, but we can still have some Q&A here. NASA has the Hubble Space Telescope that's doing some exoplanet work, including in these transiting planets. You can see the light come through the atmosphere of the planet, and you can do some spectral analysis of what's in the atmosphere. And we found several things like sodium in atmospheres of planet that way. Ground-based observations such as Keck, which does radial velocity studies, and several space-based telescopes I won't go into detail here, but that are doing different things that we can already do regarding exoplanet detection and characterization. And then we are looking for future telescopes to build. All right. What kinds of extrasolar planets are we finding, and how are we finding them? We talked about that today. Tonight, in the lecture, I'm going to go into a little bit more about what does it mean if we do or don't find life on these planets. We're within a decade or two of answering that question. What's it going to mean? What's it going to mean for our view of human significance? What's it going to mean for our understanding of what significance actually means? What is significance based on? What happens if we don't find any evidence of life and it really seems like Earth is a very unusual place? What does that mean? So there are different ways you can go with that. And so I encourage you to come to, it says tomorrow night, but it's tonight. Come to tonight's lecture in the Modern Languages Theater at 8 o'clock. I talked to you about planetary systems. Stars form in these dense clouds. It takes a few million years for it to get to a planetary system. Our theory says that we have gas giants forming first, and then the terrestrial planets, and then the rest of the stuff is cleared out. We also see during this time the transitions in the disk material. We have a disk that's originally dominated by gas, and then it turns into this debris disk, and we can observe that bottom layer more than we can observe the top level. People in my lab actually made the cover of Nature magazine by modeling with the computer what this disk of debris might look like around a young planetary system. And in fact, that was what was seen in the Fomalhaut system, as I showed you. I'm going to close up here to say this is our planet, and this is the kind of thing that we're wondering is out there elsewhere, and what it means if we find planets like that. And here's a very excited person thinking about this in the 18th century. This is my last slide. Thomas Wright of Durham was thinking about this idea that was put forth in Milton's Paradise Lost. And apparently there was an idea of many suns out there. So Thomas Wright was thinking about this. You know, what would it mean if there were, in fact, many suns out there? And he started thinking about how many there might be. So here he is thinking to himself. He says, now admitting the breadth of the Via Láctea, that's the Milky Way. So he's thinking, they already know that there's this Milky Way galaxy stretched across the sky, that they didn't know there were other galaxies yet, but he knew that there's lots of stars there. Admitting the breadth of this to be, about 9 degrees, and supposing there's about 1,200 stars in every square degree, so he's doing the math here, there'll be nearly in this area about 3,888,000 stars, and all of these are just a very small part of this great expanse of heaven. So then it just dawns on him, what a vast idea of endless beings must this produce and generate in our minds. And when we consider all these as flaming suns, as progenitors, prima mobilis of a still much greater number of peopled worlds. So now he's thinking about civilizations on all these star systems. Then he thinks about, where did this come from? He says, what less than an infinity can circumscribe them? What less than an eternity comprehend them? What less than omnipotence produce and support them? And where can our wonder cease? And I think that's the right approach. I mean, this is incredible, and I think that just thinking about this should inspire us to a great sense of wonder and excitement. This is where our exploration is going right now. So I'm going to close there, and I hope we have at least 10 or 15 minutes that we can do some Q&A. So I'd like to know what you're thinking about. Thank you. Yes. Right. I will repeat the question, and I'm also open to just questions if some of you guys are thinking about science careers or just practical things. This is supposed to be a little bit more informal than the evening lectures, but you can ask me anything. So there was one over there, yeah.
If I interpreted your comments correctly, we seem to be looking for an Earth-sized exoplanet in a habitable zone
Right.
in order to produce life. But could there not be a Jupiter-sized planet in the habitable zone?
Right, so of course there are, but the trouble with Jupiter-type planets is that they're gas giants. So we would like, they don't have a solid surface. So we would like to find a planet that's kind of like Earth in that it would have, oceans of liquid water or some kind of liquid water and an environment that's more conducive to life as we know it. Now there might be life that's not as we know it, that's drifting around in the gaseous atmosphere of a Jupiter-like planet, and so we'll certainly do the spectroscopic studies of all these things. But we have to start with what we know. We might not recognize life that's so different from our own that we wouldn't even recognize it to be life. The other thing that's interesting about the habitable zone, though, is that if you have a Jupiter-like thing in the habitable zone, it can have moons. So, and those moons can be small enough to have, solid surfaces and so forth. So the moons of our own Jupiter and Saturn in our own solar system are very interesting in their own right. We have, for example, Europa is an ice-covered moon, and even though it's outside what we would call the habitable zone, some speculate there might be liquid oceans underneath that ice that are heated from within. So, life doesn't necessarily have to be confined to that habitable zone if there's another heat source that can liquefy the water. And it doesn't necessarily have to be confined to Earth-sized planets if there's a large gaseous planet that has a moon that might be terrestrial and could support life. So. Yeah?
If the Hubble Space Telescope is taking so many beautiful pictures, how come they're decommissioning it?
Well, they aren't. That's the good news, is that I worked for years on this at NASA headquarters, and there were concerns that telescope has to be serviced by astronauts. It was designed back in an era when it was thought that the space shuttle would be going up and down every couple of weeks, So it was designed to be continually serviced by astronauts. And after the last space shuttle tragedy that happened a few years ago when a space shuttle was damaged and launched, and then it wasn't known until it landed that there was a breach in the system, and it basically destroyed the shuttle on its landing, NASA took a good hard look at the shuttle program again and realized that when the space shuttle goes to the International Space Station, which is in orbit right now around the Earth, it has a lot of options. It can park there and they can inspect it and see if there's any damage. And if there's damage, you can do repairs there, or you can send another shuttle up to rescue the astronauts. The Hubble Space Telescope is off in a very different orbit, and there's no way, orbitally speaking, for the shuttle to get from one to the other. So if the space shuttle goes up to the Hubble Space Telescope and they notice there's a problem, there's not many options for helping the astronauts to repair the shuttle or to bring them back safely. So the administrator of NASA at that time felt it was not safe to do any more missions to Hubble. Well, this was a big blow to people everywhere, astronomers and the public, because they really wanted the telescope to keep going. It was functioning fine, but it looked like in the near-term years it was going to start degrading because it needed new batteries and new gyroscopes and things like that. So several years of contemplation went on, and then fortunately, just about 3 years ago, the next NASA administrator decided that we'd come up with some clever safety advances that would allow us to take the risk, it's still a risk, but to go ahead and take the risk and send an astronaut mission up to Hubble, which we did this past May. It was very exciting. We sent a shuttle up, and last night I showed the launch and I showed some of the new instruments that we have. That should keep the telescope functioning better than it ever has before. It has a brand new camera, a brand new spectrograph, and then another camera and spectrograph that are a little bit different in their capabilities that were repaired. New batteries, new gyroscopes, and it's all set, unless it gets smashed by an asteroid or something, which I hope it doesn't, for about 5 more years of operation. And that brings us to the next telescope that NASA plans to launch. That's the Hubble follow-on called the James Webb Space Telescope. So I think we're all good to go here, and I'm quite happy about it. So. Yeah?
Why not attach the Hubble to the space station?
Mm-hmm.
Then you have that.
Right.
That's it.
So we were a lot of people thought about using the space station for a platform for telescopes, and that idea was pretty quickly abandoned. And the reason is that the space station vibrates all the time, and even if you can kind of isolate the telescopes from the vibrations and the motions, there's all kinds of sort of emissions, gas, and other kinds of things that just seem to carry along with the space stations. It's a contaminated environment for astronomy if you want to do very sensitive spectroscopy, things like that. In fact, even where Hubble is, which is apart from the space station, is not a great place for a telescope. It was put there so that it could be reached by the space shuttle, which is only orbits in low Earth orbit, we call it. The shuttle doesn't go very high, relative to the moon or something like that. But it's not great, because if you think about it, something in low Earth orbit, as we call it, things that are closer in have to orbit faster, and this thing is whipping around the Earth every 90 minutes. So the Hubble Space Telescope is a satellite that goes completely around the Earth every 90 minutes. That means half the time, almost half the time, depending on where you're pointing the telescope, you can't see what you're looking at because the Earth is in the way. So it's not a very efficient place to put a telescope. The James Webb Space Telescope, the new one that's named after a former NASA administrator, this telescope is going to be put way far in the distance, away from the Earth. That'll make for better astronomy, but it will make it impossible to service it. So it has to be built really, really good the first time, and hope that suffices for several years. Okay, we'll do here.
Just wondering, what's your take on somebody said to you, you think there's such a thing as UFOs?
Okay. So UFOs are unidentified flying objects. So absolutely there are UFOs. We see them all the time. All it means is that they are unidentified. So now that doesn't mean they are aliens, right? They're just unidentified. So most of the reports that people see, amazingly, most of the reports of UFOs come very near military bases where, odd things are often launched, or balloons or so forth, that are not advertised. So then people see something in the sky and they call it an unidentified flying object. So there are unidentified flying objects. Now, do I believe that these are alien spaceships flying over and abducting people and so forth? No, I don't. Because, quite simply, we haven't ever... these things, the sightings are all so mysterious that they can never be verified by, we need the spaceship to come and land, in the center of Toronto or something where you can actually go. And, strangely, that never happens. It's always a kind of mysterious sighting or a mysterious photograph, and then, it doesn't happen again. The elusiveness of these things are one thing that should make you suspicious. The other thing is that we have just never seen through, funded, straightforward observations of the sky, and believe me, nations around the world are monitoring the sky constantly, are not seeing these spaceships buzzing in and out. So I'm afraid to say that I don't believe that we have had spaceships buzzing in and out of our lives, but sorry if that disappoints some of you. So. Okay.
We're constantly looking, as you said, for needles in haystacks. We fund these programs and we fund the technology based upon what we know what medium supports life and what life is as we know it.
Right.
What if we're wrong?
So there could be life that's so different from ours that we wouldn't recognize it, but that's just the problem. We wouldn't recognize it. So if we're going to study, if we're going to look for life, I mean, so it does make some amount of sense to start with what you know, and so the needle in the haystack thing is I mean, certainly finding planets now is not difficult anymore. We're finding them by the hundreds. We're just honing in the kinds that we're finding. So we're finding them. The question is, are they going to look anything like Earth? Are they going to have atmospheres? Are they going to be habitable? We don't know yet whether that's a needle in a haystack or whether this is common. That's one of the things that we will find out within the next decade or two. Now, it's a little bit more than that, because life, and I'm not a biologist, so I can't answer this in great depth, but as I understand it, there are some basic sort of requirements for proteins and structures that are organics that are required in order to build up complexity. So if you want complex life, there's only certain kinds of chemistry that will support complex life, meaning that you have, molecular structure that's building up into multicellular structure, this kind of thing. And so it's not true, I don't think, that you could build life on any kind of chemical basis. There is a limit to this. There's also a limit to the kinds of pressures and things that would support complex life to develop. So there is some basis for thinking that there might not be some infinite number of ways life could develop, complex life. And in fact, we might need carbon-based, water-based life might be the only kind of life. So we don't know that for sure, but there is some astrobiological evidence and thought that this might be the case. By the way, astrobiology, there are new fields of science that are growing out of all this. When I was in graduate school, which was 15 years or so ago now, this whole idea of exoplanets was a little bit fanciful. I mean, we were just starting to find one or two, but it wasn't really considered sort of mainstream astronomy. Now it's suddenly the big deal, studying where they are, how they form. It's a big deal. And also a new field has developed called astrobiology, which is this whole study of how life might form and exist and be sustained in other environments in space. And so that this is a new, very solid field that didn't even exist 15 or 20 years ago. So. Anything else? Yeah.
How do they decide why would they think circle life is by other forms of life?
Okay, so the people in the Seti program are listening for certain frequencies of emission from intelligent civilizations. How do you decide which frequency to listen to? So that's a really good question, and it's a little bit out of my league. I don't know if you know the answer to this, but there's water. So certain. Okay, so here's our Professor Fick here could answer this better than I. There are certain things where you sort of see some very interesting feature in a molecule or something that we need for life, or something that you would imagine that maybe they could easily transmit signals that would mean something to us. But maybe you can say more about this than
They won't get this on the video.
I'll repeat.
There is two spectral lines that are very strong. One is neutral hydrogen, H1, 20%.
That's right. It's a very strong line.
Also weight.
Right.
At lower frequencies, longer wavelengths, there's much more noise. You do all kinds of things. And at shorter wavelengths, it's a lot of noise. This is a low point of the noise, and there's two very important, easy to see spectral lines. So that's considered to be a very good place to look.
Okay.
Between at H1 or at OH, in the gap between them.
Very good. So OH and H1, hydrogen, one of the hydrogen lines, are very strong lines that, in fact, we look at H1 in galaxies, in our own galaxy and in other galaxies too, to map the rotation rates of the galaxies. But these are things, or this gap between them that might be good frequencies. But it is a guess. I mean, you're trying to guess if these civilizations that are not like us, but are they like us enough to think like us so that they would think what we're thinking so that they would transmit the same way we think they might transmit? It's a bit of a puzzle. Yeah. So. Anything else? Yes?
How do you define a galaxy?
Oh, a galaxy is simply a self-contained collection of stars and gas that are sort of gravitationally bound. So the whole universe, as we discussed last night, appears to be, the space of the universe appears to be expanding. But there are pockets within that where the matter is close enough together that the gravitational force between that matter, gravity tries to pull everything together, is stronger for that local group of matter than for the larger outflowing expansion would carry it away. So we have local clusters of matter that are self-gravitating, we call it. And a galaxy is just that. It's a collection of stars and gas that's self-gravitating, holding itself together over and above this large-scale expansion of the universe. And so galaxies are pretty much islands of density in the universe, although we now know that there's in fact tenuous threads of material, intergalactic medium we call it, that's connecting these galaxies. So the galaxies are like density pits in the middle of a sort of larger web of tenuous material that's expanded over time. And so that's one of the things that the new instruments on the Hubble Space Telescope is doing, is mapping out not where the galaxies are, but where's that tenuous material that's kind of connecting them all, this cosmic web, we call it. And then there's hot gas that surrounds these galaxies that you can see in X-rays a lot. And this hot gas can sometimes show you that a whole cluster of galaxies is in fact kind of connected in the same gravitational well, we call it. So basically galaxies are islands of stars and gas, and sometimes they're embedded in larger islands of groups of galaxies.
We did start about 10 minutes late, and we've given an extra 10 minutes. I think that's great. I'm sure that Dr. Wiseman will be happy to answer any questions you want to talk to one-on-one afterwards, but I think we've actually come to the end of our time. But I'd like us all to thank her one more time for a great talk.